of the, if I may say so, shortcomings of those kinds of models uh, is something that we had already talked about. It's the fact that the saving rate and hence the ratio of consumption to income, this ratio is exogenous, and hence by definition, since savings rate is a constant, by definition this ratio is also a constant. So savings rate in the models that neoclassical models that we have discussed so far, this savings rate is constant and exogenous. So basically, by not allowing consumers to behave optimally, the analysis did not allow us to discuss how incentives affect the behavior of the economy. This is something that we have not looked into. So how would the dynamics, how would the behavioral patterns of the different agents change if we took into account the idea of incentives, right? So we did not discuss how incentives affect the behavior of the economy. So in particular, we could not think about how the economy reacted to changes in interest rates, how the economy reacted to changes in tax rates, and several other variables. Now, we had gone through the Solos-1 model in some detail, right? So there, it was shown that allowing for firms to behave optimally did not change any of the basic results of the Solos-1 model, right? So we could very well reproduce the Solos-1 model, the basic results from the Solos-1 model, if we did the same analysis in a perfectly competitive setup, right? So the main reason for this was that the overall amount of investment in the economy was still given by saving of families, and saving in turn was determined by the savings rate. That is, a portion of your income or a proportion of your income you would devote to savings. What proportion you're going to put into savings, that was being determined exogenously, right? So savings very much remained exogenous. So if we are to paint a more complete picture of the process of economic growth, we actually need to allow for the path of consumption and hence the saving rate to be determined by optimizing households and firms that sort of interact on competitive markets, right? So that would paint a more sort of realistic picture. So now the models that we would look into, the first model that we are going to look into in order to understand how the process of consumer optimization works called the Ramsay model, developed by the economist Ramsay. This particular model basically it allows for optimizing households and firms to interact on competitive markets, right? So here, when we say households, we are essentially dealing with infinitely lived households that choose consumption and saving in order to maximize their utility. And when we are referring to utility, it is dynastic utility, right? So aggregate sort of dynastic utility, which the agent, the household that is, maximizes. And when we're talking about households, it's not just one individual. There are several individuals residing within one household. Hence, the utility of a household is very much a dynastic utility rather than an individualistic utility, right? So household basically maximizes this utility subject to an intertemporal budget constraint. So budget constraint is something that we are going to look into. Okay, and the household is living infinitely what that basically means is that, suppose, one individual cannot live till infinity, obviously, but it can live till infinity through future generations, right? So suppose you pick an individual, you choose an individual, that person lives for 2 time periods, right? So the first time period, she is young, and the next time period she is old, right? So 2 time periods, and in the next time period that person's son or daughter is young, and corresponding time period that person is no longer living, but the son or daughter is old, and so on and so forth. This is how the process continues, right? Basically, we are dealing here with infinitely lived households, infinitely lived through future generations, of course, that choose consumption and saving to maximize their dynastic utility, subject to an intertemporal budget constraint, right? So intertemporal budget constraint, once again, it's a very crucial concept that would help us understand the nature of risk aversion, so to say, of an individual, whether the individual is quite prudent or whether she is not so, because how much the individual chooses to save for the future, that goes on to show the kind of risk aversion, or the kind of insurance, so to say, that the individual would choose. So the behavioral pattern, the budget constraint reveals a lot about the behavioral pattern of and the saving pattern also of the individual, right? And when we talk about the budget constraint, it's individual behavioral pattern as well as household behavioral pattern, because since we are talking about an economy with infinitely lived households, and within the economy also there are infinitely the small agents. Each agent is very similar to the other, right? So they are identical agents. So in essence, if you like integrate all these agents, then you would get the the consumption, so to say. If you integrate that, the aggregate consumption, it's basically the same as the individual consumption, right? So the aggregate the aggregate behavior of the household is exactly similar to the individual behavior, right? So now there are infinitely lived households, and they choose consumption and saving. These are the choice variables: consumption and saving. I mean, whenever you choose how much to consume, automatically your saving gets determined. Their objective is to maximize the dynastic utility, and they're doing that subject to an intertemporal budget constraint. Intertemporal meaning that the budget constraint takes into account 2 periods: the first period in which the individual is young, and the second time period in which the individual is old, right? So both time periods have to be taken into account, right? So I mean, the thing is, the individual might choose to consume a lot in the first period, in the time period when she is young, but then she also has to account for the fact that when she is old, she would not have much savings, right? So there's a trade-off, so to say. So this trade-off has to be taken care of. You have to you have to look acknowledge the fact that there's a trade-off, and then you have to behave accordingly. You have to make your decisions after taking into account how this trade-off is going to work out for you. Now this particular specification of consumer behavior is a key element in the Ramsay growth model that we are going to look into next. This was constructed by Ramsay in 1928, and later on this model went through considerable modification, because this is a pretty old model. It was later on, so to say, modified and polished, refined a little bit by Cass and Koopmans, two other economists, very renowned economists, like Ramsay. That was done much later in the 1965 actually. So once again, this the growth model that takes into account consumer optimization, that particular literature, growth models with consumer optimization, growth models that take into account intertemporal choice, intertemporal behavioral choice of behavior, of agents, and growth models that also look into the the consumer thought process in general, consumer psychology in a way, and the nature of aversion towards risk, that sort of these sort of aspects, the models which look into these sort of aspects. These models came up much later, much after Ramsay constructed the initial basic sort of framework. So one finding of very substantial finding of these kind of models will be that the savings rate is not constant in general. This is the first major deviation from the Soros 1 model that we had looked into, that saving rate is no longer constant. What is the savings rate? Savings rate now is a function of the per capita capital stock. This is something that we'll find out. So what we do is we basically modify the Soros 1 model in two respects. First is we sort of pin down the average level of the savings rate, and next we determine whether the saving rate rises or falls as the economy develops, right? So as I mentioned before, these models, the literature that deals with these particular kinds of models, in essence, what they basically do is they look into the behavioral patterns, the consumer behavior, so to say. So these sort of models have a lot of micro foundations in them. So consumer behavior, one key aspect of consumer behavior is how much you are prone to taking risks, how much of a risk averse you are, and also whether you like to save in general, whether you like to smooth out consumption in the process of savings, right? Or whether like you want to, you're more prone to taking risks. So if consumer wants to smooth out consumption, that basically means that the consumer wants a similar pattern of of consumption in both time periods, right? So for example, in the first time period when the consumer is young, the consumer indulges in a certain kind of consumption. Maybe if the consumer is risk averse, then she would want the same amount of consumption in the second time period as well. In other words, the consumer would want to smooth out consumption, meaning that she would want equal amount of consumption in both time periods, right? But if, in order to do that, definitely the consumer would like to save, a considerable amount of income in the first time period for the next time period. This next time period, consumer would not be earning, maybe should be living on pensions and stuff, and also savings, right? So saving is a crucial aspect of intertemporal behavior. And intertemporal behavior, the basic essence of these models, the basic idea of this strand of literature and these types of models is hinging around the idea of savings patterns and intertemporal pattern, right? So as as I have mentioned before, savings is a key aspect of these models, and savings is no longer constant, right? So we are going to look into the pattern, a time path that savings would follow, right? So savings is no longer constant, and savings is very much, it's a function of per capita capital stock, right? So you can normalize stuff. I'll have the lecture notes with me. The scanned version. We are going to look into it in more details, but the idea is that it would be useful. It would be handy in a way to normalize everything into per capita capital, right? Um, so savings rate is a function of per capita capital stock, which is small k. We are familiar with this, and you know you should not completely forget the Solo Swan model, because some of the ideas behind the Solo Swan model is very much used here as well. However, the Solo Swan model is somewhat modified. So it's modified in two respects. One is that the average saving rate that we found in the Solo Swan model, that was a constant saving rate. Here we have several different saving rates. So we take an average of that and we pin down that average, right? And secondly, we determine whether the saving rate rises or falls as the economy develops. So suppose the economy is going through a process of growth, right? So what we do is we look into the time path and we see how the savings rate is evolving as the economy progresses, right? So we determine whether saving rate rises or falls as the economy develops. We also learn how saving rates depend on interest rates and wealth, right? So first we'll see how interest rates and wealth and certain government policies maybe would have an impact on savings rates, and later on we would find out how savings rate would depend on tax rates and subsidies, that sort of things, exclusively on policies, right? So the average level of the saving rate is especially important for the determination of levels of variables in the steady state. In particular, the optimizing conditions in the Ramsay model. So I'm just summarizing the sort of things that we'd be looking into before plunging into the model itself. I'll just sort of give you a gist of what you would expect from the next few lectures, right? So first is the Solo Swan model that you are already familiar with. That has been modified in two respects. Now, the first modification that we are looking into, an average saving rate. Why is it relevant? Because it's important for the determination of the levels of variables in the steady state. So in particular, the optimizing conditions in the Ramsay model that we would figure out preclude the kind of inefficient oversaving that was possible in the Solo Swan model. So if you remember, this is one aspect, this is one possible drawback of the Solo Swan model, that there was a chance of oversaving, and oversaving is definitely inefficient, right? It's definitely going to lower your utility. Now, Ramsay model, if we look into the optimization of different agents, then the idea would be to choose the most efficient path, right? So this is the basic idea. So optimizing conditions, the first order conditions, when we look into the marginal marginal conditions, as in the partial derivative of your utility function with respect to the choice variables, you put them equal to 0, you figure out the first order conditions, and these optimizing conditions for the Ramsay model, basically they preclude any kind of inefficient oversaving. This is important for this is one very important finding of the model that we will be looking into. That there won't be any inefficient oversaving because of optimization, right? And this kind of inefficient oversaving, so to say, that was there in the Swan model, because the Swan model, we took the saving rate as exogenous and we did not internalize the consumer pattern. We did not internalize saving rate. We we did not endogenize savings, and as a result, the sort of behavior of the consumers in many ways, it was not efficient in a way. It was it was not utility maximizing, right? So the tendency for savings rates to rise or fall with economic development affects the transitional dynamics. For example, the speed of convergence to the steady state, that also would get affected. So if this savings rate rises with k, small k, that is per capita capital, then the convergence speed is slower than in the Swan model, and vice versa. This is something that we could figure out. Now, we find, however, that even if the saving rate is rising, the convergence property still holds under, so to say, very fairly general conditions in the Ramsay model. That is, an economy still tends to grow faster in per capita terms when it is farther from its own steady state position. This is something that we also saw in the Swan model, right? So this particular finding remains intact. So we show that the Swan model with constant saving rate is a special case of the Ramsay model. So there's a link between the two models, the Swan model and the Ramsay model. That's why it's important for us to to look into the Ramsay model immediately after studying the Swan model. So we did a bit of the endogenous growth literature, looked into one model, the AK model, but then I think that linking the two models, that is Swan model and the Ramsay model, is kind of important if we are to have a more wholesome idea of the growth literature, right? So, as as I mentioned, that there's a definite relationship, there's a definite link between the two models, the SS model and the Ramsay model. We should be able to show that the convergence property, which is something something specific to the Swan model, or like something which is sort of, in a way, you can't think of the Swan model without thinking of convergence. So that idea, that particular idea, remains intact in the Ramsay model as well. And also, what you can find in the Ramsay model is that even if the savings rate is rising, this property, this convergence property, would hold true, and it would hold true under fairly general conditions for the Ramsay model, right? So this idea that economy tends to grow faster in per capita terms when it is farther down from its own steady state position, something that was that was extremely specific to the Swan model, you would find the same result to hold true for the Ramsay model as well, right? So in fact, the fact that there's a definite link between the two models, this becomes even more clear, even more conspicuous when we are able to show that the SS model with a constant saving rate, that is nothing but a special case of the Ramsay model, right? So this further establishes the fact that there's a clear link between the two models. Moreover, this case corresponds to reasonable parameter values, right? So what we are doing is we are not discarding the solo swan model. We are rather what we are doing, we are sort of refining in a way, we are looking into. It's better to say that we are not discarding the solo swan model. We have the solo swan model at the back of our mind, but we are taking into account additional aspects of consumer behavior, right? So we are incorporating additional features of consumer behavior into our previous model. And of course, in doing so, in the process of doing that, we are looking into consumer optimization. So this is this is the first time that we are studying growth models with consumer optimization, right? So I mean, it was worthwhile to begin with the solo swan model as a tractable approximation to the optimizing framework. We also note, however, that the empirical evidence suggests that saving rates typically rise with per capita income during the transition to the steady state. That is a fact established empirically, right? So, as the economy progresses, as the economy develops, the per capita income would increase during the transition to the steady state, and typically saving rates would also increase, right? Thus, the Ramsay model is consistent with this particular pattern, and the model also allows us to assess the implications of the saving behavior for the transitional dynamics, right? So this is this is the main essence of the model. I mean, one of the crucial things that we will be learning from the model is how saving behavior changes throughout the transitional dynamics, throughout the process of uh, you know progressing towards the steady state, how the savings rate is going to behave, what would be the sort of evolution of the savings rate. Moreover, the optimizing framework will be essential later on when we extend the Ramsay model in various respects and consider the possible roles for government policies. So, such policies will in general affect the incentives to save. So, this is the basic setup of the model. So, see, the agents that we would be dealing with are firstly the households, right? So we need to understand how households behave, and households are consisting of different agents, infinitely lived infinite agents, and these agents in turn, they the consumer behavior that is that is crucial for this model. That consumer behavior is basically the behavior that's depicting the behavior of the households, right? So it's very important for us to understand how households work in this particular category of models. So this is the basic setup. So in studying the basic setup, first we're going to talk about the households and the first order conditions, the Euler equations, and the a bit of mathematics would be there. It's all involving calculus, which I'm sure it won't be a problem for you. But I would be emphasizing on the economic intuition, right, rather than on mechanically going through the mathematical results, right? So first, let's try to understand how households work, right? So households, what they do is they provide labor services in exchange for wages, and also they receive interest income on assets, right? Households purchase goods for consumption and save by accumulating assets, right? So assets, when we talk about assets, we, in essence, we mean we are referring to stocks, we are referring to bonds, and any other kinds of papers which would, give you a certain payoff, right? Um, so the basic model assumes identical households, each has the same preference patterns. In that way, they are identical, right? So identical in the sense that each household has the same preference patterns. Each household faces the same wage rate because all workers are equally productive, right? Hence, identical households, right? Um, each household begins with the same assets per person, right? And also, each household has the same rate of population growth, right? So um, the rate at which there's increase in members of households, that is same across all households, right? So I repeat, households are identical in the sense that each of them have the same preference parameters, each of them face the same wage rate, that is each all workers within each household and also across households are equally productive. Each household begins with the same assets per person, that is the number of stocks or bonds per person, and each household has the same rate of population growth. So given these assumptions, what we can do is the analysis can use the usual representative agent framework, in which the equilibrium derives from the choices of a single household. Since we are talking about infinite households, but in a very homogeneous sort of way, since each household is not different from another, from the next household, right? So in essence, we can focus on one household, right? So we can, given these assumptions, the analysis can use the usual representative agent framework. It's a framework in which the equilibrium derives from choices of a single household. So that's what we are going to focus on, the choices of a single household. Later on, we're going to discuss how the results generalize when various dimensions of household heterogeneity are introduced. But for the time being, let's get rid of household heterogeneity. Let's suppose that all households are homogeneous. Each household contains more than one adult, or it might contain just one adult also, right? So one or more adult, that is working members of the current generation. So in making plans, these adults take account of the welfare and resources of their prospective descendants, right? So when one adult, that is one working member of the present generation, when that person is making a plan, then she is taking into account the welfare of her children and children's children. So when one agent of the current generation is optimizing or making plans or making choices, then that person has to think about the welfare of the prospective descendants also, and the resources of their prospective descendants. So we are going to model this intergenerational interaction by imagining that the current generation maximizes utility and incorporates a budget constraint over an infinite horizon. So that is what I mentioned right at the outset, that we are going to deal with utility maximization subject to an intertemporal budget constraint that extends over an infinite generation, because this utility maximization is going to take into account future generations utility as well, right? And when we talk about, when we think about future generations, we are in essence referring to, generations that would extend till infinity. Like not just your direct descendant, but also, their descendants and, their children and their children and so on and so forth, right? So, So we are going to model this intergenerational interaction by imagining that the current generation maximizes utility and incorporates a intertemporal budget constraint over an infinite horizon. So although individuals have finite lives, is very important for us to understand that although individuals have finite lives, we consider an immortal extended family, right? So the extended family lives on forever, right? So this particular setting is appropriate if altruistic parents provide transfers to their children, who in turn, uh, you know, give it to their children and so on. So the immortal family that we are talking about corresponds to finite lived individuals who are connected through a pattern of operative intergenerational transfers based on altruism itself, right? So that's the idea, that all agents are altruistic, right? So because of that, the immortal family corresponds to, although it corresponds to finitely lived individuals, these finitely lived individuals are connected through a pattern of operative intergenerational transfers, and these sort of transfers are based on altruism itself. Now the current adults expect the size of their extended family to grow at the rate n. Let me specify the variables that we are going to look into. So the current adults would expect the size of the extended family to grow at a certain rate of growth of population, which is n. N is fixed because of net influences of fertility and mortality, right? So because of net influences of fertility and mortality, the rate of growth of population remains fixed at n. That's an assumption, right? So we simplify this analysis by treating n as exogenous and constant, right? Just it is a ploy to make the framework tractable, right? We also neglect migration of people. So if we normalize the number of adults at time 0 to unity, then the family size at time t, which corresponds to the adult population, that would be something that that's growing exponentially, right? So the LT would be equal to exponential of NT if n is the rate of growth of population, right? So if we are to normalize the number of adults at time 0 to 1 or unity, then the family size at time period t, that is the adult population, would be LT, is the adult population at time t, time small t, that would be exponential of NT. So if capital CT is the total consumption at time t, capital CT is the total consumption at time t, then small ct is total consumption capital CT divided by LT, that is the the total population, total consumption by total number of people present in the economy, and that is consumption per adult person. So the economy, when we talk about economy, in essence, we are referring to the household itself, right? Because all households are similar, as I mentioned before. So it would be worthwhile to look into to focus on the individual household, right? So the individual, this LT is the population at time period T for the individual household. And this is the total consumption, capital CT. So the consumption per adult member is small ct, which is a ratio of these two, capital CT and LT. Right? So this is what each household wishes to maximize. This is the total overall utility, right? So overall utility is something that needs a bit of explanation. So this is an utility that extends from time period 0 to infinity, because this is the utility of the clan, utility of the not of the finitely lived agent, but of the immortal extended family, right? So each household would wish to maximize this overall utility, right? This is an integration of U of CT, which is the current individual's utility, and the household's utility at time 0. This is basically a weighted sum of all future flows of utility, which is UCT, U of C. The function UC is often called the Felicity function because it relates the flow of utility per person to the quantity of consumption per person. So the utility, flow of utility, this is a flow, mind you, it's not a stock. So the flow of utility per person is basically it is linked to the quantity of consumption per person. So that's small c. So we assume that U small c is increasing in C and it's concave. That is, U prime C is greater than 0, U double prime C is less than 0. So, the results, just a minute. So, U prime C is positive, U double prime C is negative, and these results will be invariant with positive linear transformations of the utility function, but not with arbitrary positive monotonic transformations, right? So, in a way, the analysis depends on limited form of cardinal utility, right? So more on this, I'll talk more about this basic functional form of the utility. But the idea for the time being is that the concavity assumption generates a desire to smooth out consumption, something that I already mentioned before. The assumption that the utility function is concave, that is, the second derivative is negative, although the first derivative is positive. What this means is that the individual, the individual working member has a desire to smooth consumption over time. So, meaning that households prefer a relatively uniform pattern to one in which consumption is very low in some periods and very high in some others. So this desire to smooth consumption drives the household saving behavior, because households will tend to borrow when income is relatively low and will tend to save when income is relatively high. So basically, we also assume that this utility function UC that also satisfies the Inada conditions as before, as in the Solos-1 model. U prime C tends to infinity as C tends to 0, and U prime C tends to 0 as C tends to infinity, right? So notice one thing. I'll just wrap up very quickly and we'll talk more about it in the next class. But one thing, just try to understand that here we are multiplying the utility with the family size L, which is exponential of NT. So this, multiplication of UC by the family size, this represents the adding up of utils of all family members alive at time period T, right? The other multiplier, this, exponential of minus rho T, you probably, by now you might have wondered what this stands for. So this particular multiplier, exponential of minus rho T, involves the rate of time preference. So rho is positive, and a positive value of rho basically means that utils are valued less the later they are received, right? So in the very rudimentary Ramsay model, the very first model that came out, Ramsay preferred to assume that rho is equal to 0. So he then interpreted the optimizing agent as a social planner rather than a competitive household who can choose consumption and saving for today's generation as well as for future generations. So the discounting of utility for future generations, that is rho positive, was according to Ramsay sort of ethically indefensible. So we can work out an example with rho equal to 0 in when we do the mathematics in this chapter. But for the time being, we are assuming that rho is very much positive. It's greater than 0, and a positive value of rho basically means that the utils are valued less the later they are received, and they are valued more the earlier they are received. Right? So we assume that rho is greater than n, that is the rate of growth of population, which implies that in this equation, equation number 1, u is bounded. It is bounded if c is constant over time. Right? So I'll talk more about this. I'll explain it once again in the next class. Okay? So, all right, if you have a question on whatever we have gone through so far, you can ask me. All right then, thank you very much. We'll pick up from here tomorrow.